All right. There are still people coming in. Thanks for joining. There are still people coming in. Let's wait some seconds. All right, great. Let's start. Then thanks to everyone for coming. Welcome to our webinar. This is a insight from fabrication to analysis of perovskite solar cells. And our first speaker is going to be Justin Chen. Justin is a researcher from Stanford University, where he obtained his PhD. He has over 6 years of experience as a graduate research assistant and previously worked at the Intel Corporation, and he holds a bachelor in chemical engineering from UC Berkeley. And today, Justin is going to present this work, open air and spray deposition of HTLS for inverted architecture perovskite solar cells. So let's start with Justin. Justin, the floor is yours.
Right. Let me share. Okay, does this look good?
Yes.
Okay. Just give me a heads up if some issues occur because I do not have Teams kind of on the same screen. So just let me know, okay? But okay, I'll begin. So thanks to everyone for tuning in. Today, I'll be talking about my work, which is the scalable open air processing of the electron transport layer for perovskite solar cells. Okay. So our work is focused on the ETL. And we are focused on the inverted architecture, which means the ETL is on top of the perovskite. And so when choosing the ETL, we need the material to have certain requirements, and these are shown here. So you want the material to be N-type or electron accepting. It should have good band alignment with the perovskite. The material should be cheap and abundant, and it should be easy to deposit or manufacture. And so the materials have two types. So of course you have organic materials, and typically for the ETL, for the inverter architecture, you have C60 or PCBM. And PCBM here is essentially C60 that has been modified so it is more easily dissolved in solvent. And then after this, either the C60 or the PCBM layer, you add a BCP layer or bathocuprine, and this acts as a hole blocking layer. The other class of materials is, of course, inorganic materials. And so these are the commonly used ones: titanium oxide, tin oxide, zinc oxide, niobium oxide, and indium oxide. Now, because the ETL is deposited on top of the perovskite, we have to be very careful of the very sensitive and fragile nature of the perovskite. So whatever ETL you choose and whatever method you choose to deposit the material, the perovskite cannot be exposed to high temperature. It cannot be exposed to solvents that might dissolve it. Any chemical reactions, or for example, sputtering has energetic species that hit the perovskite. Well, this can all degrade the material. So why would someone use an organic versus inorganic electron transport layer? And what are some of the typical deposition methods? So here's a chart that I'm showing just using the same materials from the last slide. And you can see that for the high efficiency devices, many researchers will use the organic materials. This is not because the researchers are studying those organic materials by themselves, rather that they are studying other parts of the solar cell, for example, the perovskite, or maybe some interlayer or some 2D material, and they use the organic material C60 and BCP as part of their device, so they get high efficiencies this way. On the other hand, the inorganic materials, most researchers are studying that specifically for their paper. but these materials tend to give you a little bit lower efficiency. However, the benefit is that these inorganic materials, they tend to be more stable to heat and moisture, metal degradation, and mechanical fracture. And finally, if you look at the price point for the materials, the cost for organic materials is almost 2 orders of magnitude higher. And so you may be familiar with these methods of deposition. So you have spin coating, evaporation, atomic layer deposition, and sputtering. However, some of these methods may be difficult to scale or roll-to-roll incompatible. For example, your evaporation, you have to have a chamber, you have to pump down to vacuum, deposit your process, and then vent back up. Even then, by far the most common combination is to use C60 and BCP along with thermal evaporation. This is because most researchers find that this provides a very convenient and easy way to form a controlled and uniform film. However, the process being evaporation and vacuum for manufacturing can be very expensive. And just how expensive can that be? Well, several years ago, my team and I, we developed this Perovskite module manufacturing cost model. And what we looked at was a theoretical 100 megawatt plant. And we looked at the cost of the module production cost in dollars per meter squared, looking for all these things, facilities, equipment, etc. We look at it for each layer of the device. So glass ITO, your scribe, your whole transport layer, perovskite, the ETL, some more scribes, the top electrode, and then finally the rest of the steps. And you can see that for these vacuum-based steps, especially the ETL, this is very expensive, the most expensive step. And so this provided motivation for our research, and we wanted to find a way to reduce this manufacturing cost. So here our approach then was to develop this inline open air ultrasonic spray deposition of the PCBM and the BCP layer. This whole process occurs at speeds of 9 meters per minute. And so first I'll talk about the first layer, which is the PCBM deposition. So when we spray PCBM, we have to make sure that we are carefully choosing what solvent we use. We want the solvent to wet the perovskite well. So one choice is to use chlorobenzene. This is probably by far the most common choice. Many people use it to spin coat PCBM. It has a great contact angle, wets the perovskite very well. The issue with this is that the boiling point is high. And so when you are spraying the film, if the solvent does not evaporate quickly, then you are left with coffee ring features of your film. On the other hand, if you look at chloroform, which is also another potential solvent, the boiling point is much lower. However, there is some small contact angle observed. And while this might not seem to be a very large contact angle, when you are spraying very tiny droplets, these effects can be magnified and you are unable to form a continuous wet film. And so our simple solution was to just combine this into a one-to-one combination. The wetting is still very good, as well as you get a reduced boiling point. For large areas, one thing to help control the morphology is to use this near-infrared or NIR cure. So here we are using this heating module shown in the picture made by company Adfos. This is a tungsten emitter where the emission spectra can be closely predicted by that of the black body radiation. And the temperature that the substrate experiences underneath this heater is largely controlled by the distance that the heater is from the substrate. So you can go from about 250 to about 100 degrees Celsius, depending on the distance. And here are some optical microscopy of the sprayed PCBM. So for these larger areas, this is about 20 centimeters squared. If you do not control the drying, you can get these line features, whereas on the bottom picture, with the rapid thermal processing cure, we are able to get smoother features. So that was the first part, the first layer, the PCBM. And the next part I'll be talking about the spray deposition of the BCP solution. Now, this problem is actually quite challenging. The reason is because in solar cells, the BCP films are transparent and ultra thin. So they are typically underneath 10 nanometers. If they are too thin, then you have some energy barriers for electron extraction. But if they're too thick, then you can have some insulating layer. So the control of the thickness here is very important. And for that reason, many researchers typically will choose to evaporate the BCP film because they can use the in situ quartz crystal monitor, which provides feedback to their evaporated thickness. However, when you are spraying this solution, there is no in situ way of measuring the film thickness easily. And so we need a way to be able to measure after the fact that we are spraying. So we have developed methods for this. And to make our problem a little bit more simple, we are first just spraying these BCP solutions on a regular silicon wafer and performing some characterizations. And so you may ask, well, if you have a film that is very thin and is transparent, why not just use a technique like ellipsometry? Well, I'll provide some motivation. So as you may know, ellipsometry requires some optical constants. So either you measure these yourselves or you find them in literature. And in literature, we could only find one example of such. This is done by Liu et al. Some drawbacks of this technique for our analysis is that these authors analyzed films that were over 100 nanometers. And maybe for that reason, they did not include the modeling of the native silicon oxide layer that is present on a silicon wafer. This is important for us because our BCP films are so thin that when you're doing modeling, you have to include this native silicon oxide layer in your model. In any case, we decided to give this model a try. So what we did was that we evaporated our own BCP thicknesses using our in situ quartz crystal monitor. Then we took those samples and measured them with an ellipsometer and see how they compare. And so you can see that for the zero film condition, there is agreement, but if you increase the thicknesses, there is more deviation. Now this might not seem a lot, but when your film is about 3 to 10 nanometers, these small deviations can represent between 25 to 33% error. So we want to be able to do better. Again, I mentioned that the BCP layer thickness is quite crucial for your solar cell. So one technique that we've developed to use is this angle-resolved X-ray photoelectron spectroscopy. And here we're using the Stratify analysis software from the company Physical Electronics. And this helps us analyze multi-layered thin films. As you may know, for AR-XPS, essentially what happens is you can tilt the angle of your sample, and as the takeoff angle becomes more shallow, you are sampling more from the surface. So you can kind of go from deeper within the film, tilt to get analysis from more of the surface area. And the way that this measurement can be used to measure thickness is essentially using the fact of the attenuation length of material, or essentially you measure the radiation loss as the signal passes through a certain thickness of material. From that, you can calculate the material thickness. All right, so we are able to use this technique, and this is for an evaporated BCP film. But for example, you can see that there is very clear outline of the different layers. So first you have the carbon from the adventitious hydrocarbon layer on the top, and you have the carbon and nitrogen from the BCP molecule, as you can see there. Then you have your silicon oxide, and then finally your silicon substrate. And of course, this can be applied to the same thing for the spray BCP film, getting very similar results and just giving a very good outline of the different layers. And so this is one technique. We wanted to be able to have more confidence. So we decided to confirm this using X-ray reflectivity. So shown here is the data, where the data in black is the sample and the red is the simulated model fit. And this is for the hydrocarbon on the top, the BCP and silicon oxide. Now, one thing you may notice is that for the hydrocarbon layer on the top, the roughness is quite a bit larger than the actual thickness. And the second point is that the roughness of the BCP is about 2 nanometers, whereas when we measured it with the AFM, we got a roughness at about 0.2 nanometers. And so this highlights one of the challenges with X-ray reflectivity is that, for example, if you have maybe some ununiform or rough film, or you have multiple layers that can cause some weak scattering effects, you might have to have some changes in the modeling, for example, adding additional simulated layers. And so this provides a little bit of a challenge. It's a nice, quick method, but the analysis can be a little bit more challenging in the end. And then finally, we did a third technique. We put a lot of effort into making some TEM samples of our sprayed BCP film. So this is the carbon and gold palladium on the top here. And then if you look kind of in the middle, you can see the BCP and the silicon oxide layer. And if you look closely, you can maybe even see a faint line where those two layers have the boundary. And from this, then we can also use the energy filtered TEM to get some elemental mapping. So here we just kind of turn that image 90 degrees, and now we can kind of get a color representation and average thickness of the different films. So here, now the carbon signal in red gives you a BCP thickness of about 2.65 nanometers, and the silicon oxide 2.45. And one of the drawbacks of this technique is that the sample preparation involves some gold palladium sputtering, and because you're using heavier atoms, this process can essentially maybe contract your BCP film, so you end up with a result that might be a little bit thinner than you expect. So to kind of provide a quick summary of the different techniques that we use to look at the thickness, of course, you know that they all have different measurement time, different cost. Some require vacuum, some don't. It is important to also note that for the ellipsometry, X-ray reflectivity, and AR-XPS, these all require a certain kind of model, whereas the TEM does not. But it also has a hard time determining the hydrocarbon layer because it is, one, so thin, and number two, because there's some sample preparation that obscures that view. And so after these kind of considering these advantages and disadvantages, we conclude that AR-XPS provides a reliable film thickness measurement when considering precision, measurement time, and tool complexity. All right, so we are able to deposit our film and characterize it. One thing we want to make sure is that it does not degrade the perovskite in the process. So one thing we can use is grazing incident X-ray diffraction, and we are seeing the perovskite diffraction before and after the ETL is deposited. So we know that our solution and our near-infrared cure are not destroying the perovskite layer. Similarly, we can use UV-vis spectroscopy, and we see that the absorbance is retained before and after our ETL deposition. We are able to get some nice smooth morphology. So here is AFM. On the left, the PCBM and BCP, well, these are sprayed on very smooth silicon wafers. So you can see that the natural roughness is very, very low, whereas that of the perovskite is quite a bit higher. And so what happens is that when you have the perovskite and the spray ETLs, the roughness is increased a little bit. But overall, if you look at this cross-sectional SEM, this is of the backscatter mode. You can look at the ETL bilayer, which shows up as black because of the large carbon content there. You can see that the ETL sprayed film planarizes the rougher surface of the perovskite and forms a nice thin film. All right, then we can integrate it into a device and look at the performance. So here we're able to achieve a champion of over 20% efficiency, as well as we are able to do some maximum power point tracking over 10 hours. And here, you know, I am a customer, but I would like to say that the Litos light has really improved my quality of life as a researcher, just because it has really decreased the measurement time, especially when you're doing long hours and maximum power point tracking. And then finally, we do some stable operation testing. So here we encapsulated our devices and we put it under 200 cycles, going from negative 40 degrees Celsius to positive 85 degrees Celsius. The inset is the actual temperature data of our thermocycler. And even after all these cycles, it retains about 90% of its initial efficiency. And finally, another test we did was UV aging. So this is put their devices in a glove box, exposing it to UVA light up to a total dosage of about 15 kilowatts per meter squared. And even after this, the efficiencies are retained. So the point of this is to say that our sprayed ETLs are kind of meet the standard and are comparable to spin and evaporated ETLs. We did not add any extra materials or any additional capping layers to the perovskite. So we don't want to make the claim that our spray process is somehow improving the material beyond standard, because we're just using the same very basic materials. But we want to show that, for example, our spray process, we're not trapping any solvent left behind, and these devices will still have stable operation. Okay, so kind of tying back to the initial cost model, if we look at the ETL only costs, we've now decreased the cost significantly. In the red is the materials cost, and everything else besides that is a manufacturing cost. And in that sense, there's about 97% decrease, excluding the materials. However, the materials cost has increased a little bit. This is mostly because PCBM is more expensive than C60. However, one might imagine that as a small batch synthesis of PCBM is increased, you might have a drop in the materials cost. But overall, a 26% decrease is still quite significant. And so if we tie this back into the rest of the module cost, the remaining kind of steps left are these ITO and the top electrode, because these use sputter as well as evaporation, and these still have expensive vacuum costs. So that's kind of the next frontier of our group's research. Okay, so in summary, we have been able to smoothly and uniformly spray the PCBM and the BCP layer. We are able to use several analysis methods to confirm the very important thickness of the BCP. And finally, we are able to achieve high efficiency devices with our open air spray ETL process. And so I'd like to thank everyone listening for their time. These are my colleagues and my funding agencies.
Thanks a lot, Justin. This was great. Very nice presentation. And thanks a lot for being here. I know that it's very early in the morning for you. I'm sure there are going to be a lot of questions after Davide talks. Now, the next speaker is Dr. Davide Moya. Davide is an R&D scientist here at Fluxim. He earned his PhD in physics from Imperial College London, and he then spent 5 years as a group leader at Max Planck. He's an expert in materials for photovoltaics, and today his talk is going to be mixed ionic electronic conduction in perovskite solar cells, implication for small signal analysis. Thanks a lot, Davide.
Thank you very much, Daniele, for the introduction. Can you hear me well, and can you see my screen?
Yes.
Wonderful. Okay. All right. So thanks everyone for joining the webinar. So as Justin told us about, the first step when you work in perovskite solar cells is to go to the lab and make as good a solar cell as you can. The second step, of course, is to measure the solar cell and try to understand what's going on. So for perovskite solar cell, this is not generally that simple, because we often see hysteresis in current voltage measurements. We may see some suspiciously large values of capacitance or even inductive behavior in impedance spectroscopy measurements. And especially for impedance, it is quite established that this low frequency behavior that can be quite varied depending on the cell is related to the fact that we are considering a semiconducting device where we also have mobile ionic defects. And so if we want to understand what's going on and we want to make better solar cells, we need to look at this somewhat strange behavior and look at it as the tip of the iceberg. And the first thing that we need to really do is to learn a language to describe these ionic defects, because this will give us the tools to identify those processes that are actually giving rise to the response that we're observing. So in this presentation, I will give you some examples of how we can do this. So for example, I guess many of you are familiar with the description of electrons and holes in terms of electronic energy diagram. And of course, if one considers a mixed ionic electronic conductors, such picture has to be extended for example, an iodide perovskite also to defects such as the iodide vacancies and the iodide interstitials. And so we're interested in understanding the chemical and thermodynamic properties that control the concentration of all of these electronic and ionic defects. And one of these properties is the component chemical potential, for example, the iodine pressure. So we could develop, for example, different chemical models that describe the concentration of all of these electronic and ionic charge carriers as a function of iodine pressure, and this can be related, for example, to conductivity measurements, where we can deconvolute electronic and ionic components as a function of such parameter. But even such a superficially simple measurement, where we just measure a conductivity, requires a number of assumptions, and I would like to discuss this a little bit more in detail in the next slides. So what we are often working with is a device where the perovskite is sandwiched between two contacts. And for the sake of simplicity, I will consider ohmic and ion blocking contacts here. So then we may have one or two ion species, and when we perturb the system at a relatively high frequency, we can probe the ion transport happening in the bulk of the perovskite. However, if we perturb the system at a lower enough frequency, then what we will see is that ions will reach the interfaces and they're blocked at such interfaces, a process that I will refer to as space charge polarization. When it comes to electronic charge carriers, the frequency at which we stimulate the device is actually not so important on a first order approximation, but I'll come back to this later. And so these considerations are enough to already explain the simple response that we can observe when we apply, for example, a galvanostatic polarization measurement, where the fast time scales can be explained on the basis of both ionic and electronic response, while at long time scales, we only see the electronic response. Now, if we want to describe this in terms of equivalent circuit modeling, this could be a convenient and simple enough starting point. So we could have capacitors describing this ion blocking behavior of the contacts, and then an ionic resistor that describe ion transport in the perovskite. Now, this simple model already has very important implication. And as I said before, if we stimulate this device at fast frequencies, we expect that ions are not able to respond, and so we expect a linear change in the electrostatic potential in the sample with a constant electric field. While if we have a perturbation that is low enough, then we would see a reduction in such electric field due to the redistribution of the mobile ions. Now, this is a reduction that we can actually probe directly in solar cells, for example, by monitoring the magnitude of the electroabsorption signal. Such signal is directly proportional to the magnitude of the electric field in the device. And as you can see in this graph, when we go to low enough frequencies, such magnitude of electric field is decreasing. And this correlates well with a number of other independent techniques. Okay, so this means that if we want to consider an equivalent circuit model for perovskite devices, we definitely have to have an ionic branch that keeps into account all of these considerations. And then if we're considering the perturbation of the device in a situation that is close enough to equilibrium, when it comes to describing electrons and holes, we can just approximate their behavior with an electronic resistor. Now, I would like to show you how such a simple equivalent circuit model can be helpful in understanding the ionic and electronic properties of devices close to equilibrium. So this is a study that we've done a few years ago where we looked at planar devices where methyl ammonium lead iodide, MAPI, is deposited on top of a substrate where we have gold interdigitated contacts. And so this is a convenient geometry because we can carefully control the distance between these contacts as well as the width of these contact fingers. Now, when we, for example, measure the DC polarization response of these devices, what we observe is that when we change the value of L, so the distance between the contacts, the time constant for the polarization increases. And this is because the ionic resistance would be greater the longer this distance is. Interestingly, and maybe less straightforward, is the fact that the time constant also changes when we change the width of these fingers. And the reason for this is that if we really consider what this device looks like and where the capacitance that describes the perovskite metal interface lies, we can see that this is actually a distributed element, which therefore would scale with the width of the contact. And this also implies that we might be able to see the response due to ions moving on top of this contact. And so we could describe this not with a simple capacitor, but maybe with an open Wahlberg element. So the question could be, can we use this equivalent circuit model then to investigate the impedance response of such devices? And the answer is yes, we can fit the model to L-dependent impedance spectra on this side of the slide, and also as a function of the width of these gold fingers in this graph. And so you can see here that in these intermediate frequencies, we can really see this 45-degree feature, which is associated with this ionic diffusion on top of the contacts. But all in all, you can see that by developing simple equivalent circuit models, we can already establish ionic and electronic resistance and therefore the partial conductivities. All of this, of course, is relevant to the close to equilibrium situation, but we're working on solar cells, so what we want to understand is how they behave when we shine light on them. So we would like to understand how to describe these systems out of equilibrium. And to do that, of course, we need to first define a steady state condition. So here I'm drawing a energy diagram for a perovskite solar cell where we have, for example, a forward bias voltage applied to it. And then based on this steady state condition, we want to apply a small signal perturbation. So for example, we apply a small perturbation in the voltage, and then we can look at what the frequency dependent of the current that flows in the device is. And from this, we can establish what the impedance of the device is. So we can do this experimentally. We can, for example, measure bias perovskite solar cell. And as I said in the beginning of my presentation, we will have likely some interesting low frequency behavior, something that can be looking like a giant capacitor at low frequency, or also some negative capacitance behavior. And interestingly, such behavior can happen within the same device just by changing the steady state condition. An important point is that if we do a simulation, for example, with Cephus of a device, we can at least qualitatively reproduce the same behavior, meaning that the drift diffusion model already contains all the elements that are required to understand these complex features. So how can we work them out in terms of equivalent circuit models? Well, it might be tempting to maybe go back to this model that I showed earlier. It's simple enough, and it might fit at least two features of this impedance spectra that I showed. But if we think about the structure that I'm considering here carefully, here we have an electron transport material, a hole transport material, and the perovskite in the middle. These are generally, if they're good contacts, these are selective contacts, which means that we will have to take care of the transport of holes and electrons separately, also because these are now no longer in equilibrium. And then we need to consider the recombination processes whereby electrons and holes meet and recombine in the bulk or at interfaces with the contacts. Now, it's really important to understand what model to use for such recombination processes. In particular, we would like to have something that works well for different processes, and ideally that also accounts for the fact that we have mobile ions in these systems. So we can take a step back and look at what the analytical description of recombination looks like. So starting, for example, with radiative processes, this would be the expression for the net recombination due to radiative processes. And we know that this corresponds essentially to considering a diode with an ideality factor of 1. Now, if we go and look at what the small signal analysis would tell us, we need to simply linearize this expression to obtain a small signal net recombination component. If we then relate this to not the changes in concentration, but the changes in quasi-Fermi levels, which are the relevant potential when it comes to equivalent circuit models, what we find is that the radiative recombination can be well described by considering a radiative resistor in terms of a circuit model, where essentially the current that flows in the resistor between the change in quasi-Fermi level of the holes and of the electron is the small signal net recombination. Now, this resistive approach to describing recombination may or may not work well for other processes. And we can, for example, look at the trap-mediated Shockley-Reed hole recombination. And in this case, we can look at the expression of this rate and do exactly the same thing. So first of all, we know that the ideality factor of the, let's say, equivalent diode that describes this rate is not necessarily 1. It will depend on the operation, the operating condition. If we go to the small signal analysis, of course, this will look a little bit more complicated than for the radiative process. But what we can do is we can rearrange things to an expression that looks like this. And the key point here is that this small signal recombination current, let's say, is not dependent only on the changes in the quasi-Fermi levels, but it also depends on the changes in electrostatic potential, meaning that we have a current that doesn't depend only on 2 potentials, but we need something that expresses this dependence also on a 3rd potential. And it turns out that this expression is well representative also of the small signal picture for a back-to-back NPN and PNP transistor pair. So if we put everything together, if we want to describe recombination in a perovskite solar cell, but in general in any semiconductor, this would be the most general equivalent circuit model to do that. And this circuit model is essentially emphasizing that the small signal recombination can be expressed as the sum of conductance or transconductance terms multiplied by a recombination driving force, a voltage. And this voltage would be different depending on the process that we're considering. Now, this would be true locally at every point in a semiconductor. But what we want to develop is a model that is valid for a full device, which means that we can, for example, use a transmission line approach to introduce a one-dimensional model. And so for that, we need to consider the rails associated with charge carrier transport, an electrostatic rail, and all of these are connected via chemical capacitors that essentially model the storage of each charge carrier. Now, if we put all of this together, we obtain something that looks like this. Here we have the ionic rail describing transport of ions. We have the rail for electrons, the rail for holes, the electrostatic rail, and the recombination elements that I described before. Now, I know that this is quite complex, but really what this is a circuit model that is analytically equivalent to the linearized grid diffusion equations. To prove this, of course, we can validate the model by calculating some impedance spectra for a perovskite solar cell, and we can do that at different light intensities at open circuit. And we can compare what we obtain from the grid diffusion model with this equivalent circuit model for this different light intensities. And as you can see from these graphs, the results show pretty good agreement, which is promising. But of course, the problem is this equivalent circuit model can be quite complex and we have a lot of parameters, so maybe it's not helping us so much. So can we simplify it? Well, already quite a few years ago, we have suggested a model that looked like this, and this was derived semi-empirically, but it turns out that this is actually the simplest form of the equivalent circuit model that I showed earlier, based on the assumption that most of the recombination is happening at one interface. So what we have here is the very simple ionic branch that I showed at the beginning of my presentation. And assuming that ions are essentially establishing the changes in electrostatic potential in the device, we can then use a single transistor to implement this ionic to electronic current amplification, which is essentially saying if we have a variation in potential due to ion motion, we will have an out-of-phase change in current due to this electronic recombination that will change with the electrostatic potential. Now, using this model allows us to already fit nicely light intensity dependent impedance spectra and also reproduce current voltage hysteresis. So is this enough to essentially model any perovskite solar cell? Well, not quite. So there are two main points that this model might be missing, and it's the fact that sometimes recombination might be dominant in the bulk, and this model would not be able to do that. And also, as I showed in the beginning of my presentation, sometimes we not only have one low frequency feature, but we have two. So how can we reproduce these two aspects? Well, the first point can be relatively easily addressed. We can simply extend the ionic branch to a one-dimensional transmission line approach so that we can define the electrostatic potential at each point, which will drive the recombination at each point. Now, just to give you an example of how this can help us to decipher impedance spectra, we can think about, again, how the electrostatic potential changes as a function of frequency within the bulk of the perovskite solar cell. And so this is, again, going from a linear profile at fast frequency, going to a flat profile when ions are allowed to redistribute. Now, based on this model, we know that we have to identify the process whose transconductance is dominant. And in this particular example, it would be the PMP transistor. And so we need to understand which driving force will be most relevant for the evolution of the impedance. In this case, it would be this one. And so we can see that this driving force is frequency dependent, meaning that we can calculate a recombination current that is frequency dependent. And this change in recombination current can help us understand the change in impedance that we see at low frequencies. Okay, this is all nice, and it allows us to understand not only how interfacial recombination may have a frequency dependence, but also bulk recombination may have a frequency dependence. But all of this is assuming that ions only are changing the electrostatic potential in the device. But what happens if we apply a large enough perturbation that also electrons and holes are large in concentration? Well, what happens in that situation is that at very fast frequencies, electrons and holes are able to respond to the applied bias. And what happens is that at fast frequencies, we don't have a linear change in electrostatic potential, but we have rather a slightly more complex profile. We recover the linear profile in electrostatic potential only when ions can redistribute within the bulk. So we have an ambipolar diffusion process happening in the bulk, which is then followed by the space charge polarization effect that I discussed early in this presentation. So essentially the point where we have this change in electrostatic potential that becomes flat in the bulk. So this essentially means that we have two regimes, two different polarization processes at low frequency. And indeed, this will provide two transitions for the dominant recombination driving force. And this is reflected in the impedance that we calculate for this system in 1 and 2 changes in the low frequency recombination current and therefore recombination impedance. Now, this effect can be well reproduced if we consider a simplified version of the circuit that I showed before, but not with the simplified version that does not consider the effect of electrons and holes in the determination of the electrostatic potential. So this quite complex, but not quite as complex as the circuit I showed before model allows us to discriminate the various time constant that determine the response of a perovskite solar cell. Okay, to conclude, I gave you one example of how understanding the defect chemistry of mixed conducting perovskites is quite important to then set the foundation to understand their response also out of equilibrium. I presented an equivalent circuit model that is analytically equivalent to drift diffusion in the small signal regime. And finally, I showed you how all of these low frequency behavior that we see for perovskite solar cells can be attributed to space charge polarization, but also to ambipolar diffusion, or also referred to as stoichiometric polarization in the bulk of the device. And all of this needs to be taken into account when developing appropriate models. With this, I'd like to just quickly thank people from Max Planck Institute in Stuttgart, as well as people at Fluxim in the R&D software and hardware department, and also people from Imperial College in London, and of course, all of you for your attention.
Thanks, Davide. It was great. And strangely, today we have plenty of time for questions. So let me start reading. Okay, this one is for Justin. Does the solvent mixture recipe for the ETL also work for the spin coater?
I haven't tried to do it one-to-one chlorobenzene and chloroform on the spin coater. I think part of the reason is just because chlorobenzene spin coats so well. It's so easy. I think everyone uses it and typically has success with it. I haven't really heard anyone specifically try to tailor the solvents for spin coating unless they have some maybe like environmental concerns or reasons. Certainly I've seen for like, there's some people who've done like slot dye or spray. Oh, actually, yeah, some other people have done some spray, but the people who have done slot dye, they will definitely try to change the solvent. It seems that chlorobenzene is only really good by itself for spin coating.
Right. There's Antonio. He's asking, do you think that the setup you described can help increasing the reproducibility of the sample fabrication? And he's also asking if you have any statistical analysis of your stability measurements.
Yeah, so the spray process with good control, it can have high uniformity as well. It can also be, if you hook up a lot of spray systems together, it can be quite a large range of processing area. For the statistical of stability, yeah, we had some, I just showed some small, maybe they're asking about, yeah, we have some pretty tight error bars, so I think overall it's pretty okay. Hopefully that answers their question.
Yeah, I think so. They're also asking if you could share the composition of the perovskite.
Yes, we use quite a mixed one. It's by a researcher named Qi Zhang. They're based out of the NREL, but it's basically like a 4 cation. So there's a little bit of rubidium, some cesium, some methylammonium, and formamidinium, and a little bit of bromide and iodide. And the concentration is about 1.5 molar, so it's quite thick. And I think a lot of people who are achieving kind of the higher efficiencies now are using like a much thicker concentration, high concentration, because you can get, something about 800 nanometers of perovskite, and that will really help boost your current. But of course, the fill factor can be difficult to also keep high at the same time.
Thanks. We have plenty of questions for you, Justin. This one, interesting. How to overcome the challenge of pinhole using spray coating method for thin layer PCB deposition? You have a layer of PCBM under the PCB. Is this intent to avoid the leakage from the PCB pinholes?
Yeah, if I understand correctly, yeah, the pinholes are definitely challenging. I think for us, it was less an issue of the spray itself, but more about like the keeping the dust out of and particles. We had like an enclosed chamber, but I think we prefer to have had like a clean room to have done this. Unfortunately, we did not. So that was actually our biggest challenge, was just a lot of particles from outside. And I didn't really understand part of the question, but the BCP layer is important because it helps kind of reduce the energy barrier between and otherwise the top electrode and the PCBM.
Great. Okay, let me ask a question to Davide, so you just can take a breath. Davide, based on your discussion, is it possible to tell? Is it possible to tell if a certain impedance spectrums can indicate that this solar cell is good or not? Just by having a look at the spectrum.
Yeah, so this is it's a bit difficult in the sense that if you have a solar cell that is perfect, so we are at the radiative limit and all the recombination is radiative and transport is efficient, then you would expect that ion transport within the device is not introducing any frequency dependence in the recombination. So this would mean that you would just see one semicircle, just like a silicon solar cell or a traditional semiconductor-based solar cell. These low frequency features can be taken as a sign of where your limitation is. So these spectra can tell us which recombination process is currently limiting your performance. But this is not necessarily also telling you if your solar cell is very bad or very good. As I said, probably only if your cell is very close to the radiative limit and you know that that's the reason you see a single semicircle, then you can comment. Otherwise, you need to do a bit more analysis.
There's a question I'm not sure. Probably this is for you as well, Davide. The obstacle now for Perovskite is the instability. Can the model help on that?
I like to believe so, in the sense that, once again, if you can tell why you're seeing a specific electrical response, so if instead of just measuring efficiency, you maybe do intermittent current voltage or intermittent impedance spectroscopy, then you can see which aspect of your solar cell is changing as a function of aging. Now, if you're able to identify where that strange low frequency behavior comes from, and you see that that is what is changing, then you might also be able to understand whether you have an interface that is degrading, or if you have transport that is becoming worse, or whatever other possible source of degradation. Of course, there may be situations where the model is not able to directly point you to that. But of course, a very good starting base is the most important point. Yeah.
And now, Justin, back to you, so Davide can breathe. From the cost breakdown that you showed, Justin, the material is the most expensive parameter for the ETL. And do you think that there are other organic materials that have not been tested, that can do the work? Can you comment on that?
Yeah, I think the so by far the most popular are C16 PCBM. There is a possibility of having a different material. I think at the end it comes down to synthesis and small batch synthesis and the kind of the economies behind that. I think part of the reason why I said that if kind of, for example, there's large scale manufacturing, maybe the PCBM manufacturing will be in a larger batch, and then kind of as you take advantage of the economies of scale, that price point can come down. But right now, if any of your researchers know that when you purchase it online, the price per gram is quite large. So certainly, if there's a new material that you can synthesize very quickly and cheaply, then that will benefit. But off the top of my head, I'm not aware of kind of anyone who has chosen to tackle that problem just because the available materials are so simple.
Mm-hmm. Great, thanks. A couple of more questions to Davide. How do you fit the impedance curve? Have you used the fitting software, or you build the simulation?
So for the very simple equivalent circuit model that I showed, I wrote my own code to essentially calculate the impedance. And for the one with the single transistor, I did the fitting manually because getting a fitting procedure to converge was a bit tricky. It's probably something that can be improved. Yes, so that's essentially. I guess one of the issues in these situations is that you have a lot of parameters potentially, and you might not have a single solution to your fit, or it will depend how you define your minimum.
There's another question on the model, if this model works for 2D perovskites as well.
I would imagine so. I suppose the question is whether your two-dimensional system requires an additional dimension in the model to describe some specific property that cannot be sort of projected into a one-dimensional model. But the same type of approach would essentially apply to any, to be honest, to any semiconductor, with or without mobile ions.
All right, great. Thanks to everyone who joined. Thanks to Justin again. Hopefully you will have a break now. And thanks to Davide. Our next webinar is going to be a topic that we didn't focus on till now. It's going to be very interesting, optimization, large area solar cells and LEDs from Swansea University. This is going to be on July the 9th. We are going to send you some additional information later on. Thanks again to everyone, and I will see you the next time. Bye.
Thanks.
Thank you. Bye-bye.
Bye-bye.